delete this 5 for that and then 5 for this. So if you just look at this, so the 6 square minus 26, this takes care of the ascending order. And if I twice that one, it will be the total number of permutations. Yes, Lakshmisha.
Can you scroll up?
Yeah.
Scroll up to the question.
Yes.
We need the number of arrangement for the 6 cards in which any one can be removed, leaving the other in ascending. We're not reintroducing it at all. We're only just
No. What I'm saying is that see this identity permutation, that is 1, 2, 4, 5, 6, for instance. So this could be got in several ways. That's what I'm saying. This could be got in several ways. Okay, let's see what's path. Yes,
So I used the same method which you did and got it correct.
yeah. So this the thing is, if what we want is we want the arrangement of 6 cards. That is, I have my 1, 2, 3, 4, 5, 6. So this is the identity arrangement. How many ways I can get this arrangement? So in this, I can either remove 1, then also it is the ascending order. Remove 2, ascending order. Remove 3, ascending order. Remove 4, ascending order. Remove 5, ascending order. Remove 6, ascending order. So I can this arrangement will be counted 6 times totally. Okay. Similarly, a thing like 2 and 3 interchange like this will be counted twice. That is 1, 3, 2, 4, 5, 6. This arrangement can also get from, see, this arrangement code, this arrangement will result in an ascending order if I either remove 3 or remove 2, both of them. So I can't count them twice, right? I have to count them only once. So I have to delete for 5 of them, and then similarly for this one, identity arrangement is counted 6 times, so I have to delete 5 of them, because if I remove all the 6 of them, then their identity arrangement will not be counted at all. That's why I have to arrange 5 of them. Okay, so let's Lakshmi Shah. You had yes doubt. Yeah, go ahead, Lakshmi.
Oh, okay. I think the question is basically if you remove one of the cards, it will yield ascending order. If you remove 3, I missed it 1 for anyone. If you remove anyone, I thought. I think I made a mistake.
No. If you remove one of the cards, not
So
any
you
one.
can remove 2, you can remove 3, and it will still be an ascending order.
Yes, that's correct.
1, 3, 2, 4, 5, 6 can be removed to 1, 2, 4, 5, 6 or 1, 3, 4, 5, 6.
Yeah, so that arrangement will be counted twice in our order. Meaning when I do this, meaning deleting and re-entering, that arrangement will come twice. That's why I can't do that, right?
Yeah,
Okay,
if you delete, but why do you have to reintroduce?
No. What do you want to know? See, I want 6
Why?
cards.
If you are deleting a number, why are you introducing it again?
See, I think no, I have to be careful. See, what I want to count. Our thing is to count all arrangements of 6 cards. All arrangements of 6 cards. This is what I have to count. So how will I get such an arrangement? I am finding a method for getting that arrangement. What is that arrangement? I just remove a card and reintroduce it elsewhere. So that means that arrangement will satisfy this property, isn't it? So what we have done here is that
Oh yeah, if you remove a card from the identity permutation,
reduce. Yes.
1, 2, 3, 4, 5, 6. If you remove a card from identity, the permutation, and you put it somewhere else, it will automatically get counted.
Yeah.
So what happens is all the number from 1 to 6 and place K in any of the 6 spaces. So the number of arrangements will be 6 square.
Yeah,
Oh, okay, but
that is the key. That is the key. In this 36, how many times the identity permutation is counted? Because what we do is that to come up with the arrangement, we follow this method. Okay, that's it. Because of the method, these things come in. Yes, Parth.
So I just wanted to tell Siddharth why it was we are adding 1.
What do you mean we are adding 1?
Like he asked the question why after we are subtracting 5 we are adding 1.
Why we are adding 1? We are not adding 1. See, we are counting this. We are counting the. We are
Oh,
counting.
here in this part. Oh,
See, we are
Okay.
counting in this one. See, there are 6 times the identity permutation is counted. So I have to count it only once. Since I have counted 6 times, I just subtract 5 times.
Yeah, yeah, yeah.
Yeah, yeah. Yes, Lakshmisha.
Okay, so when our permutation is just the identity, we are overcounting it 6 times.
Yes.
And when I and I plus 1 are swap places, when the two numbers are swapped, it's counted twice. We have I can vary from 1 to 6 minus 1.
Yeah.
Why?
What?
When the second part, when I and I minus 1 are swapped, this part right here.
No, no, no. When I and I plus one are, for instance, let us look at this permutation. That is 1, 3, 2, 4, 5, 6. In our method, so in this, the key is that this method which we adopted to find all the permutations. So in this method, I can get this one in two different ways. One is that from this identity of 1, 2, 3, 4, 5, 6, I can just delete this and then reintroduce it after this one. That way
Oh,
also the same
or
permutation.
you can delete 3 and reintroduce it after 2.
Before two, yes, that's right.
Okay, but then
But no, the
it
whole
is counted
no, the
twice.
whole over counting happens because of this method. So if we have a different method of coming up with all these permutations, there is no need to over count at all. You can get it directly as well. Okay, because of the
So
method
that
which we adopted here,
because of
we
the
have to
method we adopted here, we have to everything is counted twice. So
yeah,
basically it's 1, 3, 2, 4, 5, 6. So basically you can do 1 and 2, or 2 and 3, or 3 and 4, or 4 and 5, or 5 and 6.
yeah. So
Yeah.
those 5 of them are each counted twice. I have to delete all those over countings. I have to delete one of them, so I am deleting 5 of them. Okay. And what about the others? I think there was one Anushka. Yes, Anushka.
Could you scroll up to the question, please?
Yes.
Yes, thank
Lakshmi,
you.
you remove these things, please. Yeah, let me clean this up for you. Yes. Yes, Anushka.
I didn't have a doubt, sir. I just
Hmm.
wanted to write it down.
Okay. Next one. Okay. This is a trivial one. I mean, all of you must have got it. So how many 5-digit numbers are there such that all have distinct digits? So I have to fill 5 places. So the first place can be filled in any one of the 9 ways because zero is not allowed there. And then once I have done this, zero is allowed here, so I can fill it in 9 ways. I can fill it in 8 ways, 7 ways, and 6 ways. That's all. Yes, yes, Lakshmi.
Okay, so just scroll up.
Yes,
I understood the thing, but identity permutation. Why are we subtracting 5 for identity permutation?
for the
If we are
previous.
counting just identity permutation,
No, that's what I
why do
said.
we count it 6 points?
No, 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 that's what I said. See, how do we? No, I think you have missed how I am coming up with all the permutations. What I am doing is that I am following a method. What is that method?
Okay,
Just
so
start with the
basically what you
identity.
are doing is when you exclude the number and place it again in its own position, you get
Yeah, I get
identity
the
permutation.
same thing. I
There
get
are
the
6
same thing.
such occurrences. So we
Yeah,
need to subtract 5. We need to
everything is. This is counted.
subtract 5 when you delete the number 2 and again place it back in its own position.
Yes.
That's why we get 26 and times 2, 52 is the answer. Fourth question is actually pretty easy. 9 times 9 times 8. Only thing is, shall I tell you what's tricky? To find. I've written everything haywire. I better go and find my fourth one.
Yeah, this day once we had some question.
Sir, for the
this thing this question, the digits, I think is the fourth one.
Hmm.
That one I got a completely different answer.
What is that?
Like it is something along the lines of 87,696.
Hmm?
87,696, something like that.
87,696. How?
Yeah, the number of ones which have all unique digits. For some reason, I got that.
First of all, how many 5-digit numbers are there?
There are, I think, 99.
Hmm?
1 second, sir. I'm
How
not sure
many
exactly how much, but
how many 2-digit numbers are there? There will
how many
be
two-digit
90 of
numbers? 99. Wait, not
90 of them.
90.
90. So 3-digit numbers will be 900.
900.
Right?
Yes,
4-digit
sir.
number will
But
be so total
yeah,
90,000 numbers will be there. 5-digit numbers. Out of which you are saying that some 80,000 etc.
yeah, sir.
is.
But
No, no, but
so
how
what
did
I
you get it? Let me know. Yeah, get. How
so
did you
what
get it?
I did was I considered two cases. We
Mm-hmm.
have the number which has contains a zero, or it doesn't contain a zero.
Okay.
So if it contains a zero, then
Mm.
first we look at the other four digits.
Mm-hmm.
So that will be since the digits have to be unique, we will have 9 to 8 into 7 into 6 for the other four places. And the
Mm-hmm.
zero itself can come in four places because it cannot come in the beginning.
Okay.
Like we can imagine it like four blank spots
Yeah,
where
yeah.
the other four numbers come, and zero can come anywhere but here, like in any of these gaps.
Okay. Fine.
That's what I did.
Mm-hmm.
Then after that, I I got
Look at zero, meaning
I
which does
considered
not
a
contain
case with
zero.
yeah I
Ah.
considered a case where it does not contain a zero.
Mm-hmm. So
So I had done this.
it will
Again,
be
there
9
are four
into
digits.
8 into 7 into 6 into 5.
Yeah.
Ah. So if I add these two, I'll get this.
Oh, yeah, I think I made an error with part B, sir.
If I just now, if
I missed
this
something.
is the
Yeah.
second part. So if I add, this is the non-zero thing. So this is zero thing and this is a non-zero thing. If I add these two, 9 into 8 into 76 is common, and 4 plus 5 is 9. So this is the same number.
Yeah, I got something completely different.
Yeah. Okay. Right. So this is yeah. Remove this, please. 10 chairs are arranged in a circle. Find the number of subsets of this set of chairs that contain at least three chairs. At least three chairs. Okay. At least three adjacent chairs. Right. So, did anyone get it correct? Yes, but
So mostly I have got it correct. I'm just checking it.
so what's the answer did you get?
I got it as 581.
581. Yes, that's correct. Okay. So how did you do that?
So first so now we know that we have a subset with less than three chairs, and it should not contain three adjacent chairs.
That was okay. Then
So we know that. So now if there are 10 sets of three chairs, so that there are three adjacent chairs.
mhm,
Correct. So now there are 10 subsets of four chairs where all four are adjacent.
very good. Mhm,
So 10, then we do 10 into 5 or 50
mm,
where there are only 3.
mm.
And if there are 5 chairs, then
No, no.
then
What about in the case of four chairs? Three are adjacent, the other is not.
what's up?
Now, in the case of four chairs, three will be adjacent, the other is not. How did you count that?
Yes, sir. Like I am using combinatorics here, like, and then I'm like now if we have set, I'm doing it somewhat like this. I have here, then something like this. So now one of them is for. So now I can't annotate, so I don't know why, but somewhat like this. So.
No, no, no.
Huh.
So there, no, no. The method, okay. The method is fine. The thing is, first of all, I have to look at all the three chairs are adjacent. I have the set is only three elements, four elements, five elements, six, seven, eight, nine, and 10 elements. So these are the different cases I have to consider. If I have three element subsets, all the three has to be adjacent. Suppose if I just number the chairs as 1, 2, 3, 4, etc. up to 10, the number of such subsets is 1, 2, 3, 2, 3, 4, 3, 4, 5, etc. up to 10, 1, and 2. So there are 10 of these. Then if I have four of them, three must be adjacent. So three of them must be adjacent. The remaining, all the four are adjacent is basically again 10. So all the four are adjacent is 10 sets are there. Only three adjacent, the remaining not adjacent. That also is a set which is satisfying this condition. So three are adjacent. The fourth one has to be this one and this one should not be there. The remaining thing I can choose any one of those five sets. So this is I know that the three are adjacent number thing is 10. So and I can choose any one of the five in 5 ways. So there are a number of elements of four element subsets which have three adjacent and the fourth is not adjacent. Fourth is not adjacent is 10 into 5, that 50 sets. Already I have 10 which are for the 60 sets. So the four element subsets are 60. Three element subsets are already know it is 10. Similarly, five element subsets we got to count for all of them. So let's look at this we already know. So five chairs that all the five are adjacent in 10 ways. And then all the four are adjacent. All the four are adjacent four. And I can't choose this one and I can't choose this one. So I got six gone. So remaining four. So 40 have four adjacent. So and again, so three are adjacent, the remaining two are not adjacent, meaning the remaining two could be anything other than this one. So I can have 5C2 ways, I can choose any two of those chairs. I don't care whether they are adjacent or not adjacent. So again, there are 100 chairs like this one. So 5C2 into 100, 3 adjacent. And 6 adjacent, all the 6 are adjacent 30 ways, similar thing. Similar thing. So if you add all of them, you get 405 subsets. And up to 6 months. So, and all possible chairs with more than 6 chairs will have at least one group adjacent anyway. So I can choose 10C7, 10C8, 10C9, 10C10. So that gives 176. So add all these. Yes, there was a doubt. Who is it? Parth? Who is that? Who raised hand?
Sir, I raised hand. I just wanted to say I'm very bad at explaining.
Okay. Okay, no problem at all. Doesn't matter. So this is actually here what we do is that we do something called the case analysis. We call the case analysis. That's how we do this problem. Yes, the Siddha. Yes, Lakshmisha. Yes, Lakshmi.
Can you scroll up
Roll up.
immediately to the next slide?
Yeah.
Okay, enough. Okay, that's all.
Anushka.
No doubt.
Anushka.
Sir, I don't have a doubt. Even I wanted you to scroll up.
Yeah.
I got it. Thanks.
What about Parth? I think he was he one more raised. Isn't it?
Yes, sir. I just wanted to say that do I send my solution in the chat?
Hmm. Okay. Okay. Now there is one more way to do this. That is. Uh, okay, that will be long way. No, don't worry about that. So I have to do this. So all subsets, etc. Okay, no problem. Yeah, that's correct. Yes. Right. So let's look at the next one. 25 of King Arthur's knights are seated at the customary round table, and how many ways 3 of them can be chosen such that no 2 of the 3 are seated next to each other. So I have to choose 3 of them, and then I should such a way that no 2 are seated next to each other. So in this case, the easiest thing to count is that the complement. So the complement. So what is the complement of that? So no 2 must be seated next to each other. So what will be the complement? Either all the 3 are seated next to each other, or 2 of them are seated next to each other. Like that, isn't it? So let us look at how many ways all the 3 are next to each other. That is very easy. So same as the previous problem. So 1 to 25. There are 25 ways in which all the 3 are seated next to each other. 2 of them are seated next to each other. The remaining is not. This is 2 can be chosen, and then this cannot be chosen, and this cannot be chosen. So there are remaining 21 are there. Remaining 21 are there. So similarly, if I choose 2 and 3, and I have another 21, so it will be 21 into 25. Because there are 25 ways of choosing 2 adjacent, and 21 and 25 ways of choosing exactly 2 adjacent. The remaining is not adjacent. So I have to delete these cases from the total thing. So how many ways I can choose 3 out of 25? This is the total number of sets. 25 choose 3. This will be 25 into 24 into 23 by 1 into 2 into 3 minus 25 minus 21 into 25. So if we can do that, this is 4. So this is 2300 minus 25 minus, what is this one? This is 25 and 50. So 525. So 525. So if I just 550, so 2300 minus 550, so it will be 0571750. So that will be the number of ways of choosing 3 which are not no 2 are adjacent. Okay, it's a simple problem. Only thing is here we note that we count the complement, because complement is easy to count. Okay, right. So this one we did a similar problem. This could be done as in the first problem. So I can just keep on counting how many ways I can reach here, and so on. So if you do that, so you can get this number, meaning this kind of answer. All these things would be reached in one way. This could be reached in one way. So note that I can't go diagonally here, only by right and up. So this will be this one is 2, and this is 3, and so on. So here it is 10. From here I can go only like this. Here it is 20, and then I can come to this one from here also. That this is 30, this is 65, this will be 65. So if I do that, it is just that. Okay, that is one way of doing that. The second way of doing that is, note that I can go to the tops, meaning top grid, only if I reach either this or this or this, and then from there move like this. Okay. So what I can do is that I can find out the number of ways of reaching A to P1, and I go only one way this way, and the number of ways of reaching P1 to B. Okay. The number of ways of reaching A to P is, there are 2 steps right, 1, 2, 3 steps up. That means it will be 5C2. 5C2 ways of reaching from A to P, and then one way of reaching P1. And from here I have 1, 2, 3, 4, 5. Again, this is 5C2. So this 5C2 into 5C2 ways of reaching via P1. The next one is reaching via Q. So this will be 1, 2, 3, 4, 1, 2, 3. So this 6C3. And then once I do here, it will be 1, 2, 1, 2, 4C2. Like that. So if I add these 3 things, I can get the same answer. So that's what we have done here. So the first Q1, so 6C3 into 4C2, etc. If I add all these 3 things up, then I get again 325. So the main thing is that we are counting how we reach the top grid, and from there how you reach the final point. So that's what we are counting here. I can reach from here or here or here, and note that I am counting only the first time it is reached here, P1. For instance, Q1 could be reached from P1 also, but I'm not counting that, because that will be counted as part of this P1 path. So I count only Q1 by coming from here. So that's the thing. So we have to be careful about that. So one, I can reach P1, P1 or R1, and from there I can reach B, and I have counted that way. And this also is okay, this also is okay. So both are fine, right? And 325. Okay, the next one. 10 books are arranged in a row. In how many ways can we choose 4 non-adjacent books? How many got it right? How many got it? The ones.
Sir, I think this I used this as a solution.
Huh?
I added a dummy block at the end after 10,
Uh-huh.
like here.
Hmm.
Then I imagined each book to be like some sort of a block. In
Mm-hmm.
other words, every block is like this one.
Mm-hmm.
So the left side is a book,
Mm-hmm.
and the right side is just like to represent the empty space. It
Mm-hmm.
has to have at least.
Mm-hmm.
So then after that, I just counted the number of ways
Yeah,
to
but we
arrange
haven't
this.
okay, we haven't done how to arrange the number, arrange it.
Yes, sir, but it's not that tough actually. I managed to do it.
Yeah, yeah. If you know that the Mississippi problem, then this is easy. But I don't want you to use that. Can we do it from simple things which we taught so far?
Yes, sir. But I used this as a solution.
I use the solution. What about the other one?
So
Oh,
you had given this problem in RMOTP, so I remembered this answer.
yeah.
So in this, what I did, I now if those we have to arrange four books so that none of them are adjacent. So and we have a total of 10 books.
Hmm.
So now if we
Hmm.
arrange 1, 2, 3, 4, 5, 6 books in center, and
Hmm.
then I don't know how to explain, but then we should get 7C4, which is 35.
So why 7C4?
So because we are adding dummy place at the right, so hence we have 7C4.
No, we are not adding dummy place at all here in this case. Okay. Raghav.
So my method is a bit similar to Parth's
Hmm.
method. So what I did, I read the 4 books which are not to be kept adjacent. I named them A1, A2, A3, A4, and the
Hmm.
other books B1 till B6.
Hmm.
So between B1 and B6, I kept slots, empty slots, and before B1 and after B6, I kept more 2 slots.
Hmm.
So in total, I got 7 slots. So now
Hmm.
in those 7 slots, I can place any of the 4 books. So
Hmm.
then they will not be adjacent. So the
Yeah.
number of total ways we can choose 4 books which are not adjacent
Hmm.
will be 7C4.
Yeah. That's correct. So okay, what others? Lakshmi. Yes.
I didn't get the answer and I didn't understand anything. But what basically your thing is you are putting like 1, 2, 3, 4, 5, 6, 7, 8. Is it something like this? I
Hmm.
don't understand at all what they are saying. Put the
No, no.
books in the gaps. What
No,
gaps are they talking about? And what books?
one minute. See, let's look at. Suppose I have removed 4 books. I have removed 4 books from the 10 books, so that no two are adjacent. Okay. How will that row look like? That row will look like some gaps here, right? That is a gap here, a gap here, and a gap here, and a gap here. That means I will have 6 books remaining. I 6 books remaining. Depending on the number of, depending on the where the books have been pulled out, I will have a gap at 4 places. Two gaps these 2 gaps will be adjacent. They won't be, because if these 2 gaps are adjacent to each other, that means there is no book in between these. That means I would have pulled out 2 books which are next to each other, which is not the case. So what I have here is, if I look at this bookshelf, meaning book row, after the books have been pulled out, it will be like six books will be there and 4 gaps will be there, and the gaps will be in between the books. So I can create the same environment in having these 6 books in a row, and then looking at the gaps in between. How many gaps will be there? There will be 7 gaps in between. If I have 6 books, I'll have 5 gaps in between and one before and one after. So if I remove those, so what I have to do is that I have these 6 books here, which are in a row, and then I have to introduce gaps corresponding to the books that are removed. So I could have introduced it here, or here, or here, or here, these 4 places. Similarly, any 4 places among the gaps have been chosen, I would have recreated this gap business. That means if I have, let us say, n books, and I have chosen k books, that means I have the remaining thing are n minus k books are remaining in the shelf, but they will also have n minus k, what? N minus k plus 1 gaps in between. There will be n minus k minus 1 gaps in between, and then one at the end, one at the other one. So I could have chosen any one of those gaps to put the books back again. So this will be the number of ways of putting back again. So this means that if I have 10 books, choose the remaining 6 books. There are 7 gaps in between them. Choose the 4 gaps, and that's what it is. Okay, this is the quickest way of doing that. There are other ways also, like path did that Mississippi problem and so on. We haven't discussed that, so we won't do that problem. So here it is. Suppose I have 100 books and I choose 5 of them, so that no two are adjacent. What will be that? The remaining are 95. Right? This will create 96 gaps. 96 C5 ways will be the one which will be this. Okay, no two are adjacent. Right? Okay, so let's look at the next one. This most of you would have done. A simple case by case. So Lakshmi, shall I remove this please? Anushka? Oops. Yes, Anushka. Anushka. Let's look at
Sir,
yeah,
could you scroll up 1 minute
this one.
to the previous problem solution?
Yeah.
Yes, thank you. Yes, you can proceed. Thank you.
So here I have a train compartment. Okay, Anushka. Okay, Parth and Sai. Okay, Parth. What's the question?
So nothing.
Okay. You got okay. Lakshmi Shah got it anyway. So about what about the others? Like Sai, I think there was
Sir, I
more.
don't have a question. I want to answer this. Answer the ninth question.
Yeah, you know the
Okay.
answer.
Yes.
Okay, so this is basically what we do is that we just first of all take care of by case where this mother and the child are sitting. Okay, that means we divide the possibly into 2 groups, whether the boy and his mother are face the engine or they have their backs to the engine. Okay, so first let us determine the first case. So I have this mother are facing the engine, right? That means this is the engine, let us say. Here it is the engine. And then how many seats are there? I have to be careful. So 2 rows of 5 seats. Okay, so 2 rows of 5 seats. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. And then what I have here is that the boy has to be sitting in the window here. So this is my window. Mother has to sit here. The remaining thing is the 3 passengers who want to face the engine there are only 3 seats, and then this could be done in factorial 3 ways. Okay, this is the arrangement, correct? And the remaining 5, so the remaining 4 passengers can sit in how many ways? So any one of the 4 passengers, the first one can sit in any of the 5 ways, second one can sit in any of the 4 ways, third one can sit in 3 ways, fourth one can sit in 2 ways, which is same as 5 into 4 into 3 into 2. So with any of these, that is factorial 3 into 5 into 4 into 3 into 2, because this is AND. That's why you are multiplying. So this factorial arrangements for the mother and son and other 3 and the remaining. So this will be first one. The number of S2 again, first place the, so again we have to place the mother and son like this. So it's the son and the mother. And I have these 3 places and these 5 places. Right? And we first place the 3 passengers in the seats facing the engine. From here, I can choose 3 seeds in 5C3 ways, and then I can place them in factorial 3 ways. Okay, so which will be same as 5 into 3 into 2 by 1 into 2 into 3 into 3 factorial. Okay, which will be same as 3 factorial. So 5 into 3 into 2, which will be 30, I believe. Yes, 30. Yeah. So, and then which, okay. The other one, the remaining 5 seats for the remaining 4 passages could be done again in any number of 5 into 4 into 3 into 4 into 2 again. So we just multiply that out and add these two things. So it's simple case by case analysis. And okay, this one is a bit tricky. So given n points, no 4 which lie in a circle and no 3 lie on a line, find the maximum number of points of intersection of the set of circles determined by all triples of points belong to the given set of n points. Yes, Parth.
So I had to read this question about 30 times to get what it meant.
Oops. How many others read the question 30 times? Huh? So did I give n or did I give 10 points? What was the question I gave? 10 points I gave or n points? Yes, Raghav. Yes, Raghav.
So you give 10 points.
I gave 10 points. Okay, no problem. We'll do it for n together so that it's
And it's
easier.
also easy.
Yeah, so then who else? Okay, only Raghav. Okay, done. Okay, n is also easy. So there are two ways basically. Let's do both of them. So one is that, see, any 3 point, no 3 points are collinear. That means I can find a circle through any of those 3 points. So I am given totally n points. So I can choose any three points in NC3 ways, and there's a unique circle passing through them. Okay. So every set of 3 points among the remaining n minus 3 points, I have already chosen 3 points. The remaining n minus 3 points are there, and any 3 will also again will determine another circle. Okay, that will be n minus 3 C3, and then they will intersect in two given points. Okay, so this gives us n minus 3 circles through this one, so they will intersect in 2 points. So therefore, what will be the yeah, so these n minus 3 circles will each add 2 new points to the intersection points. And there is one more thing also. So I will get 2 points out of this n minus 3 points and add one of these points. Add one of these points, and then that will intersect in one more extra point. That will intersect in how many points that will intersect? Yeah, that will intersect in. So okay, sure. Let me explain it again. So I divide this into two cases. One is that I take 3 points, and then the remaining n minus 3 points, I take n minus 3 C3 circles are there, and each circle will intersect in 2 distinct points. That means these circles will get 2 into n minus 3 points will be the points of intersection. Okay, and what will happen is that I can also take 2 of these n minus 3 points and then add a point and take this circle, and this circle will intersect this circle already in A, and then one more point in one more new point. So this will intersect in n minus 3 C2 points. N minus 3, see, this will circle in one point like that. Since I have n minus 3 C2 and I can take either A, B, or C, I have 3 times n minus 3 C2 new points of intersection. So this is, so I have added these two, isn't it? For different from A, B, and C. Okay. Now each intersection point will be counted twice in this. So I have NC3 circles in the beginning, and each circle will determine these one intersection points. And then if I do this one, then multiply that one, and each point will be counted twice. So I have to divide by 2. So this will be the number. And I already have original n points, so this will be the sum of these two. So this will be the total number of new intersection points, which are their distance circles and so on. For instance, if I have 5 points, if I have 5 points, so what will be the number I should get here? If I have 5 points, it will be the original 5 plus 5 into 2 into 5 minus 1 divided by 3 into 5c5. 5c5 is 1. So I have 5 plus, this is for 2 into 9. So 5 into 9 by 3. So there will be 15 points, new points I should get. Let's see whether I got 15 new points. So I have all the red points are marked the new points. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Sure enough. So I get 15 for if I start with 5 points. Similarly, we can do. So this is one way of doing that one. The other way is much simpler. What we do is that we first form all the circles, NC3 circles. And any two circles could be chosen in NC3C2 ways, isn't it? NC3C2 ways. Okay. So those two circles, those will intersect in NC3 2 points because I have NC3, one circle here and one circle here. So these will intersect in those many points. So I have NC3C2 ways because any two circles will intersect like that. Okay. So this counts each new intersection point once, but it will overcount all the given endpoints because this point will be counted. How many times it will be counted? This point, and then whenever I have a n minus 1 C2 as the other 2 points forming the circle, this will come on the circle as well. So it will be counted those many times. To just have so A will be counted n minus 1 C2 ways. This will be just 3 and C4, and we subtract that and we are done. Okay, this is other way of doing that. It's slightly more, what should I say, sophisticated argument, but this is quicker. But the other method is also works in any case. Okay, right. So what are the other problems? So only that. Yes, but
Sir, before this camp, I had learned a formula n into n minus 1, where n is the number of circles. So I used that only to get my answer. Is it okay?
yeah, that's okay, not a problem. Whatever. Okay, so that's what those 10 problems. Hope all of you got most of them right, and even if you didn't get it right, but hope even the try you make is good enough. This chat thing. What is 7 by 10? No. See, don't do that. See, don't meaning grade yourself in all these things. See, we are not here to grade, we are here to learn. Okay. So don't grade, and note that in all the cases, meaning there is not even one single occasion in which we use something which we didn't learn in the class. That is just about meaning addition principle, and then multiplication principle, and NCR, and of course factorial n and so on. So these are the only things which we use. And then note that how difficult, meaning how many difficult problems could be solved using just these basic things, right? Okay, right. So let's look at some more things which are interesting in their own right. We saw this NCR. What is this NCR? The number of ways of choosing R from n objects. This is what it is, right? And most of you would have learned about what is a plus b whole square. So a square plus 2ab plus b square. A plus b whole cubed, a cubed plus 3a square b plus 3ab square plus b cubed. And similarly, a plus b whole power 4, it will be a power 4 plus 4a cubed b plus 6a square b square, etc. It's the binomial theorem. Okay. So what happens is that if I take a plus b whole power n, I have a plus b into a plus b, etc. up to a plus b. I have n factors here. And then suppose I want the coefficient of a power r into b power n minus r. What I have to take is that I have to choose r of this and take a from that factor, and the remaining thing will be b. That means this will occur as many times as I choose r factors from n. Therefore, this one must be NCR. So that's where the whole thing comes from. My a plus b whole power n is NC0 into a power n, NC1 into a power n minus 1 into b, and so on. So that's why these are called the binomial coefficients. Okay. This has lots of nice properties. Let me, so if I just take with a and b means it is 1. The second one is 1, 2, 1. The third one is 1, 3, 3, 1. I just add these two. This is 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, 1, 7, 21, 35, 35, 21, 7, 1, and it goes on like that. So this is actually what is called the Pascal's triangle. This is called the Pascal's triangle. So here we saw that this one is sum of these two, correct? This is actually 4C1 plus 4C2 is equal to 5C2. So what I had here, 4C1 plus 4C2 is equal to 5C2. So more generally, we have NCR plus NCR plus 1 is equal to N plus 1 CR plus 1. Okay, NCR plus NCR plus 1 is equal to N plus CR plus 1. So this is very easy to prove. Okay. And more than that, we want to prove something more interesting than this. So this anyway, you can easily see. Okay. Let me show you one nice property. Suppose I add all these four numbers. What do you get? 1 plus 4 plus 5, 15 plus 20, it is 30. Okay. So similarly, if I add these three numbers, I get 21. If I add these numbers, I will get 50. Okay, so this is actually what is called the hockey stick identity, which is don't annotate this. So this is actually equal to what we have here, what we had here. So this is 4C4, this is 5C4, this is 6C4, this becomes 7C4, right? 7C5. So what I have here is that MCM plus M plus 1CM plus M plus 2CM and so on up to NCM. If I stop like this is N plus 1 CM plus 1. So that's what we have. For instance, 4C4 plus 5C4 plus 6C4 will be 7C5. That's what we had here. So 4C4 plus 4C5, sorry, 4C4 plus 5C4 plus 6C4 is 7C5. Like that. So how do you prove that? How do you prove this one? It's a very important meaning. It's a very nice problem.
Use the Pascal's identity.
Huh?
This uses the Pascal's identity. R choose R plus N choose R plus 1 equals N plus 1 choose R plus 1. Okay, so what we kind of wish is this 4 choose 4 and 5 choose 4. We want to basically turn it into a form like 5 choose R and 5 choose R plus 1.
Okay.
Right?
Yes.
Okay, but here we have the denominator is the same, but the numerator is different. 4 choose 4 can be written as 5 choose 5, I think.
No, 4 choose 4 plus 5 choose 4 could be written as what?
5 choose 5. 4 choose 4, 5 choose 5, right?
4 choose 4 plus 5 choose 4 only again.
And 5 choose 5 plus 5 choose 4.
5 choose 5.
Ah, I get it now. So basically 4 choose 4 is 5 choose 5, right? 4 choose 4, 5 choose 5. 5 choose 5 plus 4 choose 4. This is in the form n choose r and n choose r plus 1. We get 6 choose 5. And that 6 choose 5 we add it to 6 choose 4. We get 7 choose 5. We get 7 choose 5. And on and on and on. It keeps continuing.
That's one way of doing that. I'm going to give you a proof of this directly without using that kind of inductive step and so on. So what I'm going to do is that I'm yes, but yes, but
Yes, sir. So I have a proof. So using combinatorics, if we do LHS is equal to RHS, then if we see LHS, then if we do m factorial upon m factorial 0 factorial, so it becomes 1, and then m plus 1 factorial upon m factorial into
1 factorial.
m plus 1 factorial.
Mhm.
Yeah. So like that, if we go on, then we will get some values, and then if we simplify n plus 1 and see m plus 1, then we will get the same value in a shorter note if we
Yeah,
take.
that's all lots of hand waving. But anyway, so let me okay. There is an important technique called counting in two ways. Counting in two ways. What we will do is that we'll find a quantity and then count it in two different ways. One will lead to the left hand side, the other will lead to the right hand side. Then you would be done. Okay. So listen carefully. This is a very important technique, and it actually has plenty of combinatorial identities in a quick fashion, proven in a quick fashion. Now let's look at the right hand side. Can you find an equation which will be equal to the right hand side? What is this n plus 1 c m plus 1? So is it not? Suppose I start with this at 1 to etc. up to n plus 1. So how many subsets are there? How many subsets of this set with m plus 1 elements? Exactly. How many subsets will be there? I have totally n plus 1 people, out of which I have to choose m plus 1 means the number of ways is n plus 1 c m plus 1. So I already have counted this one. So this is equal to the number of m plus 1 subsets, the m plus 1 element subsets of this set. Say s is equal to 1, 2, etc. up to m plus 1. Okay. Now I'm going to count the same thing in a different way. What I'm going to do is that suppose I have A is a subset of this, which contains m plus 1 elements, m plus 1 elements, okay, m plus 1 elements, right? So then this A will have one large element, right? The largest element of A. Suppose the largest element of A is n plus 1, because it could be any one of those. Largest element of A could be n plus. If it is n plus 1 is the largest element, means n plus 1 is already in A. So how many more elements I have to add? I have to add one. I have already have this n plus 1 is already there. I have to add m from this guy. I have to add m from this guy. Therefore, I have mcn. So there are mcn elements. Sorry, there are ncn subsets with n plus 1 as the largest element. Similarly, if n is the largest element and I have to add 1 to etc. up to n minus 1, from there I have to add m elements. So it will be n minus 1 c and so on. Since it already has m plus 1 elements, it can't be meaning no elements, and it could be all the m elements must be already there. Otherwise, we won't have this one. The largest element would be m. In this case, it will be just MC. So what I have here is that if the largest element is m plus 1 here, or m plus 2 and up to m plus 1. So this is the left hand side. The left hand side and right hand side both count the same thing. What do they count? They count the number of m plus 1 elements subset. So we are done. So this is the expression which we got by considering the largest element of m plus 1, that subset. And this is, so this one is the set which n plus 1 is the largest element. Next one is the n is the largest element. Next is the n minus 1 is the largest element. This is the set in which m plus 1 is the largest element. If m plus 1 is the largest element, the m more elements are there. They should have to be chosen from 1 to m only. That is MC. So they are done. So this way, I have counted this in one way, this in the other way, and both has to be the same thing. So n plus 1 is m plus 1 is this. Okay. So this is so this kind of these kind of proofs are called either the counting proofs or using combinatorial arguments. These are called the combinatorial proof rather than algebraic proofs, which can again be given. So most of the combinatorial identities like this can be given combinatorial proofs like this or counting proofs like this. That's more charming in any case most of the time. Okay. So anyway, so that is that's an aside. So far good going. At least even if you do 5 or 6 problems, it is still fine. But you have to appreciate that you have learned very few tools. But even with that, you can do very complicated problems like these. Okay, that's the moral of the story. Right. So from tomorrow we will do something else, and I hope most of you would have created those 4 cubes and then colored and tried that game or not yet. Stacking the cubes. Yes, Lakshmisha.
I make the cubes and it's quite hard. These cubes, it's quite hard to make stacking. I still haven't made a stacking arrangement yet.
Okay. Yes, Parth.
So I wanted to make it, but I could not because I was writing the notes of all your lectures.
Okay, no problem at all. But anyways, I can try because we still have tomorrow, and then we will settle today. And then tomorrow we will discuss that problem. That is what is called the instant insanity. The one which you are going to discuss is called the instant insanity. It's a very famous problem. And in fact, there used to be as I showed you that 4 cubes, it's also called 4 cubes problem. Okay. Anyway, so don't look at the net to see the solution. Okay. So otherwise you'll spoil the fun, right? So just look at these 4 cubes and then try to stack them and then find out whether you can stack them in the correct order, right? So we will see tomorrow, and we will discuss that, and tomorrow and day after tomorrow we will discuss that. In fact, we will discuss 2 solutions to this problem. Okay, right? So then see you tomorrow. Bye bye.
Thank you, sir.